problem of our time. And the plan put forward by EU's Project Destiny is the clearest vision of how we can help tackle climate change as a challenge. Together with the help of our collaborative partners, NVIDIA can help make that vision a reality. While the importance of global warming is not new to any of you, it's clear that something recently has changed. Our estimation of the severity and immediacy of this threat has been shaken by recent events. Over the last several years, frequent weather disasters across the globe have demonstrated that dangerous impacts have arrived. There have been fires, floods, heat waves, droughts, mudslides, and tropical cyclones, with a frequency and severity never seen before. They've occurred in every country, at every latitude, in both hemispheres. No nation and no region of the globe is immune, and the damage that's occurring appears to be far greater than our best models to date had predicted. The cause is no mystery. We know that climate change is caused by greenhouse gas emissions, primarily from our extraction and burning of fossil fuels like oil, coal, and natural gas, but also from livestock production, agricultural waste, transportation, cement and steel production, heating and cooling, and widespread deforestation. We also know the solution. Combating climate change is primarily an act of political will. Governments across the globe need to choose to enact legislation to reduce and eventually ban the use of fossil fuels. In its place, we need massive expansion of renewable energy resources. We need to incentivize sustainable technologies. We need massive infrastructure projects to modernize transportation, agriculture, manufacturing, and to adapt our cities to be more resilient to disasters. These efforts will raise costs, so income assistance will also be required to offset them. And since we all live on the same planet, wealthy nations need to assist poorer nations to develop their energy resources responsibly and to avoid further deforestation and wetland loss. If history is any guide, governments are unlikely to act until disasters have become so frequent and so expensive, it's clear we can't afford not to act. Unfortunately, at that point, much of our funding will go into rebuilding and recovery rather than prevention. In this chart, you can see the rising number of multi-billion-dollar disasters in the US in recent years. We now have about 20 per year instead of just 3 or 4 a few decades ago. In any case, once governments do decide to act, we'll find ourselves in a race against time. We already are, in fact. With each degree of additional warming, the number of disasters will increase exponentially. Once action is mandated, it's ultimately industry and academia and government that will need to make this transformation happen. Collectively, we will design and build the solar power plants, carbon capture facilities, ocean desalination plants, and smart cities. But how are such things accomplished? Through an iterative process of modeling, production, and improvement. By doing as much of this as possible in simulated environments using digital twins, we can speed up the process and minimize the costs. Modeling and simulation will play a critical role in every activity designed to fight climate change. Models are needed to predict the impacts of climate change. They can accelerate the design of new sustainable technologies and the discovery of new materials for energy storage and transportation. We can use simulations to optimize complex systems and to provide intelligent feedback and control. Observation will also play a major role. The Earth is surrounded by a high-quality satellite and sensor network that can provide detailed feedback on current conditions. With these observations, we can detect and track wildfires, tropical storms, and other natural disasters. We can improve search and rescue and detect harmful greenhouse gas emissions. Observations are also critical in data assimilation, which is important for weather forecasting. So we're beginning to see some movement toward large-scale climate action. For example, the European Union and UK have enacted legislation designed to achieve carbon neutrality by the year 2050. Part of that effort includes a large-scale modeling initiative called Destination Earth. Its goal is to design digital twins of the planet that we can use to understand and combat climate change. Destination Earth is just one of several important climate modeling initiatives. For example, the Vulcan climate model is dedicated to accelerating climate science by better exploiting the world's fastest supercomputers using modern programming languages, machine learning, and open source collaboration. CLIMA, the Climate Modeling Alliance, expresses similar goals. And the brand new NSF initiative, LEAP, seems focused on AI techniques in particular. Project Destiny provides an appealing vision of what the future of Earth system modeling could become over the next decade. It describes intuitive user interfaces, responsive answers to what-if questions posed by decision makers, high-resolution storm-resolving models, unified open access to satellite observations, and energy-efficient exascale computing to power it all. While Destiny provides a highly ambitious vision, it just so happens that NVIDIA's technologies are a perfect match for making this vision a reality. For example, NVIDIA's Omniverse can provide the real-time interactive experience needed to make digital twins intuitive. To make the models responsive and fast, we can build AI emulations of the world's top weather and climate models. Physics-based models, now referred to as Earth engines, will be as important as ever. And with the help of NVIDIA's new Grace CPU, we can train those models in record time. All of this can be powered by NVIDIA's SuperPods, which are some of the most capable and energy-efficient systems on the planet. Destiny envisions digital twins that are as intuitive and simple to use as any app on your tablet. Omniverse can make this happen. It can provide real-time ray-traced environments that enable you to interact with a digital twin as if it were the real thing. It can also operate as a central nexus for standardized access to models, data, and observations. The video on the right, which doesn't play that smoothly in this Zoom chat, shows a sample of weather model data rendered in Omniverse. An important goal of a digital twin Earth is to explore the impacts of a given decision. For example, you might ask which regions of your country will experience increased flooding under a given climate emission scenario. Today, answering such a question might take weeks. However, it is possible to generate near real-time results through data-driven models and emulations. This was first demonstrated by the WeatherBench project, which trained a ResNet model to produce near instantaneous medium-range weather forecasts. NVIDIA enables this layer of Destiny by providing a full-stack solution for training AI models. In destination Earth terminology, physics-based models, called Earth engines, are as important as ever, and they are the only sure way to generate accurate physical predictions of climate conditions that haven't yet occurred. In fact, these models will need to be pushed beyond their current limits to hyperscale resolutions of 1 kilometer or higher in order to fully resolve storms without convective parameterizations. Additionally, we can build digital twins to model other important subsystems like forest fires, floods, power grids, as well as biological, social, and economic systems. Enormous AI projects and GPU-accelerated HPC models traditionally have been limited by the bandwidth between the GPU and CPU. NVIDIA's new ARM-based CPU, called Grace, overcomes this limitation by tightly coupling the two together. This gives 30 times the bandwidth and 10 times the performance when training these giant models. Grace represents a major breakthrough in the types of models we'll be able to build and train. Once fast data-driven digital twins have been trained, they can be coupled together, which opens up a whole new realm of possibilities for exploring complex system interactions. And this is precisely what's needed to answer what-if questions posed by a decision maker. For example, a climate emulation could provide initial conditions for a weather emulation, which could then provide wind and cloud predictions for power plant models, which in turn could be used to optimize our electric grid. When models are fast enough, both one-way and two-way coupling of these models is possible. One can imagine going a step further. Instead of a user manually testing one configuration at a time, we could employ reinforcement learning to optimize our system, given a set of financial, legal, and social constraints. For example, one could launch an automated search for the best possible placement of, say, a seawall, the best distribution of wind and solar power plants, or the optimal transportation system, or electric power grid. NVIDIA's technologies can help in the operational phase as well. After these systems have been designed and deployed, NVIDIA's Jetson Edge devices can provide the intelligent feedback, control, and coordination necessary to ensure their safe and efficient operations. Although it's most obvious how NVIDIA's technologies can contribute to climate and weather modeling, the same basic principles can be applied to each of the important climate focus areas listed here, including climate mitigation, adaptation, and monitoring, as well as disaster response, climate justice, and potentially geoengineering. In this final section, I'd like to review some of our ongoing research collaborations and show how they fit into this larger vision. NVIDIA is working with industry and academic partners across the globe. The number of collaborations we have is vast. Since I don't have time to discuss them all, I'm just going to focus on a handful of projects in which I'm personally involved. In Europe, I'm working closely with our industry partner ATOS, as well as major climate and weather centers such as ECMWF and DKRZ. In the US, I'm engaged in projects with major climate and weather centers, including NOAA, NCAR, NASA, and Oak Ridge National Lab, as well as the NSF Institute called AI2ES for short. In my opinion, one of our most exciting projects is our new effort investigating full model emulation. In collaboration with ATOS, we're working to construct AI replicas of global weather and climate models based upon the WeatherBench dataset from Rasp et al. And the related work by Dale Duran's group at the University of Washington. Once trained, we estimate that a 10-day forecast at 10-kilometer resolution could be produced in as little as 13 seconds on a single GPU, in contrast with operational models that take roughly an hour on 100,000 CPUs. This would represent a potential speed up of up to 30 million times. Currently, however, an emulation at 10 kilometers remains theoretical, as there are significant technical hurdles that need to be overcome to build a model of this size, mostly the training data. So what's the advantage of making a model like forecast like this instantaneous? Well, weather's chaotic, and using physics-based simulations, we can only afford to simulate a handful of ensemble members. This sample is very likely to miss many rare but highly impactful extreme weather events. Instantaneous forecasts would enable us to explore thousands of ensemble members, more accurately detecting and quantifying the risks. At present, the highest resolution achieved in full-scale emulation has been about 1 degree or 100 kilometers, due in part to the limited quantities of training data available. But can we push past this limit? With enough resources and innovation, I believe we can. Potential avenues of advancement I'm excited to explore include transfer learning, physics-informed neural networks, active learning to generate data on demand, transformer-based models for scalability, and generative models for producing more accurate atmospheric states. Increasing the resolution of a physics-based model takes many years of work. In contrast, building a more sophisticated data-driven model is simply a matter of compute resources and scalability, as demonstrated by the amazing GPT-3 language model and its successors. Physics-informed neural nets can greatly reduce the amount of data we need by adding physical constraints back into the system. This can provide the best of both worlds. NVIDIA SimNet is a tool for implementing these for multi-physics simulations. It isn't currently set up for climate and weather simulations, but in principle, it could be adapted for that purpose. Each member in an ensemble forecast needs to be analyzed to detect and track extreme weather events. In collaboration with ECMWF and NOAA, we're working to move automated tropical cyclone detection from research to operations. AI detection of cyclones will be faster, more accurate, and more robust than existing heuristic techniques. When combined with a large ensemble, we can provide a far better statistical assessment of the likely track and behavior of these dangerous storms. We can use similar techniques to monitor storms on the surface of the sun in an effort to predict impactful space weather. Working with the Heliphysics group at NASA Goddard and Altamira, we trained neural networks to detect features using data from the Solar Dynamics Observatory. NVIDIA's AI painting technique uses partial convolutions to repair damaged images. Researchers at DKRZ, NVIDIA, and UF Berlin realized this same technique could be used to fill in missing climate observations as well. We used transfer learning from reanalysis datasets and fine-tuned it on the HADCRUP 4 climate observations. This model was able to accurately reconstruct global gridded observations as far back as the year 1850, giving us a more accurate estimate of global temperature change. This work was published in Nature Climate and was included as part of the recent IPCC assessment. Together with ECMWF and ATOS, we're working to improve weather forecast data assimilation by removing persistent patterns of temperature bias. Employing satellite occultation as ground truth, more accurate atmospheric temperatures can be determined after the fact. Using this as a ground truth signal, we've trained neural networks to remove this temperature bias. NVIDIA's collaboration with NOAA is very active. We support NOAA's Hera supercomputer and help organize NOAA's AI workshops some of the time. Perhaps most importantly, we run a series of hackathons where we provide dedicated assistance to NOAA's researchers looking to improve their AI and HPC codes. We also support individual research projects across NOAA. Our most active collaboration to date has been with NOAA's Global Systems Lab. This team works on a wide variety of research topics, including AI-based cyclone and convection detection, as well as improved fire, radiative transfer, and soil moisture modeling. For further details, check out the talks by Christina Kumler and Ryan Lagerquist. Another important organization NVIDIA supports is AI2ES. This large NSF-funded team focuses on trustworthy and explainable AI methods for the environmental sciences. For details, please review Amy McGovern's talk and tune in to session 2A on trustworthy AI. The last project I'm going to mention is a modeling collaboration with Matthew Norman and Murali Meena at the Oak Ridge National Laboratory, where we trained neural networks to learn subgrid scale turbulent dynamics. This super resolution model reconstructs fine details from a coarse CFD simulation. As you can see, with the aid of a ResNet model, we're able to accurately match the fine-grained turbulent structures produced in the high-resolution large eddy simulation. So, in summary, climate change is upon us, and really, we have a limited time to act. NVIDIA is interested in doing what it can to help. We like the ambitious visions of forward-looking projects like Destiny, Vulcan, Klima, and LEAP. And we think we have all the pieces, both hardware and software, to make these visions a reality. I personally plan to focus a lot of my attention in the near future on important challenges in this area. So thank you for your attention. And as always, please feel free to contact me at dhall@nvidia.com if you have any interest in collaborating or any questions for me.
Thank you so much, David. We have one question. Let's begin with some more information about Omniverse. Is this mainly a simulation or rendering engine, or is it doing something more than that? Can you give us a little more detail about that, please?
Yeah, it's a great question. I'm sorry I didn't have time to go into it in detail, but Omniverse is a remarkable platform that we are developing that has a lot of capabilities. Real-time rendering is a very big piece of it, so you can make realistic looking things in it. But also it has the ability to build user interfaces that are customizable. So it becomes a front end for basically any application you can think of. It also has powerful collaboration capabilities. So you can plug in your other codes, your other models into it, creating connectors, and they can transfer data between these things and between people working on different models. So there's really a lot to Omniverse, and I don't really have time to explain all of its possibilities, but please look it up online. You can see that it has the potential to be a front end for basically, and a way to integrate basically everything that we're trying to do. User interface, models, data, everything.
All right, thank you for that. Any more questions? Please send them to Slack channel 3, Weather and Climate. Here's a good question. A challenge for data-driven forecasting is extremes. Do you have a strategy for getting those right, given that there won't be as many in the observations?
Yes, extremes are, of course, the thing that's of the most interest. And there are a number of things you have to do to get this right. The most important thing is when you're training AI networks, you have to have a balanced set. So you have to collect all of the extremes and make sure your data is very carefully balanced. But also, generally, you might not have enough data at all to capture those extremes. So then you have to use other tricks. One of them is transfer learning, where you get the model really close to the right answer using other data, and then fine tune it on these extremes. Another possibility is simulations. Find a weather climate model that can simulate these extremes and then use that for transfer learning as well, so that you can, again, get very, very close to the right answer before fine tuning on this data. Between those three things, you can generally do a pretty good job, unless you have no examples at all, really.
All right. And our final question is, what recommendations do you have for uncertainty quantification in data-driven methods?
Yeah, so uncertainty quantification is a big open problem. A lot of people are working on it. There's 4 or 5 different methods that are being used right now. None of them are perfect. But just to give you an example of how it might work, you can imagine training a neural network, then training 5 or 10 of these same neural networks. When the neural network knows what it's talking about, all these models are going to agree. When the neural network does not know what it's talking about, it's just wrong, it's going to give random values. By comparing this ensemble of networks together, you can see when there's a large spread in the prediction uncertainty and when there's a small spread. This is, of course, just one type of uncertainty, but I'm assuming this is the type we're talking about here, the uncertainty in the model prediction itself. Other types of uncertainty can be captured as well, and there's lots of techniques for doing that, Bayesian neural nets and such.
We're definitely going to hear more about that this week. Thank you so much again, David Hall, and everyone for your questions. We're moving on now to our next speaker, Chongxing Fan from the University of Michigan. And he will be talking about using different machine learning algorithms for clear sky detections, in infrared hyperspectral observations, assessment, and physical interpretability. Take it away.
Thank you. So hello, everyone. I feel honored to have the opportunity to share my research here. So today I'm going to introduce our work on using different machine learning algorithms for clear sky detections using different in infrared hyperspectral observations. So the problem of clear sky detection is of great significance in multiple applications, including data simulation for weather forecast, trace gas retrieval, and clear sky flux estimation. A common approach to perform the detection is to use images like MODIS, which has a fine spatial resolution but limited spectral channels. So these clear sky detection algorithms are often based on both visible channels and infrared channels. There's another category of tools called hyperspectral remote sensing, which refers to using a hyperspectral sounder to retrieve information about the atmosphere and the surface. Hyperspectral sounders like AIRS can obtain radiances in thousands of spectral bands of narrow bandwidths. So it can be beneficial to combine the advantages of high spatial resolution of MODIS and high spectral resolution of AIRS and train a robust machine learning model to distinguish clear sky cases solely based on AIRS radiances. Plus, by applying interpretation techniques, it is possible to obtain valuable underlying physics under abundant spectral information. Therefore, our goal in this study is straightforward. We wanted to use machine learning to perform clear sky detection purely based on the thermal infrared spectrum without the use of any spatial and temporal information. 3 popular conventional machine learning models and 2 neural networks were trained and compared to 2 physically based algorithms, which use simple physical rules to perform the classification. Here, SST refers to sea surface temperature, while BT refers to brightness temperature from AIRS observations. These ML models are among the most popular and robust models that can work satisfactorily in many fields. We deliberately limited the information available to thermal infrared channels and sea surface temperature when training models. This is to assess the potential of utilizing the information embedded in the full infrared spectrum in the case of cloud classification. We used AIRS brightness temperature from 1,598 thermal infrared channels as our primary predictors and Hecquart sea surface temperature as the auxiliary predictor. Models were trained against series MODIS cloud flags. We selected only native view and tropical ocean samples for the sake of easy training. Due to the differences in series and AIRS footprints, a collocation strategy shown in the figure is used. Bigger circle represent series footprints, while small field circles represent AIRS footprints. From the satellite observations, it is evident that cloudy samples are far more frequent than clear samples. Thus, we sampled the dataset to equate the frequency of 2 classes and perform other procedures such as normalization and hyperparameter tuning following the standard machine learning guideline. We trained all models on the equally sampled dataset at year 2004 and evaluated them on the full dataset at year 2008. The table shows the results from the 5 ML models and 2 empirical models. And we showed the true positive, false negative, true negative, false positive, as well as the accuracy of these models here. The numbers in the brackets also indicate the ranking of these models with respect to the performance, from good to bad. We found that all machine learning algorithms, once trained, can outperform these 2 physics-based algorithms. Linear support vector machines and 1D cAN are slightly better than others from the perspective of all the metrics here. Even though the cloudy sky cases are far more frequent by the ratio of 19/1, by pre-sampling the dataset for training, we achieved a decent balance between cloud detection rate about 81% and the clear sky detection rate about 91%. One interesting thing here is that both empirical methods have a perfect detection for clear sky cases. We can see no false positive samples here. The reason can be found in this histogram, which shows the frequency of clear sky and cloudy sky cases with respect to the difference between SST and maximum BT. The thermal contrast algorithm is based on the fact that many thick cloud tops emit long-wave radiation at a much lower temperature than the sea surface temperature. If we set a threshold to be 10 K, as these dashed black lines, we can decently separate these thick clouds to one side. However, there are also a portion of clouds that do not have a high thermal contrast. Those cases are troublemakers that are confused with clear sky samples. And then we performed the feature importance analysis to highlight significant predictors. We plotted the feature importance of each channel as the x-axis with respect to the channel's corresponding peak height of the weighting function as the y-axis. So you can understand the weighting function as how much radiance is emitted from each altitude. So we also marked CO2, H2O, and window bands as red dots and other trace gas bands as blue dots. The importance of the SST feature is marked here as 0.01. Results show that channels with weighting function peak on the ground as well as the SST have relatively greater importance, especially for CO2, H2O, and window channels. This suggests that all machine learning models have identified these channels consistent with the physics of thermal contrast. This is further supported by the fact that all high thermal contrast samples are perfectly predicted by all machine learning models. A follow-up experiment also shows that although SST is determined to be significant in prediction, removing SST has little impact, at least on 1D cAN's performance, because it can find surrogates in the spectrum for SST. So this implies that we can, purely based on Ayres radiances, to achieve a decent performance of machine learning prediction. To inspect the source of prediction errors, we took advantage of EOS WordView API and coded a simple interface for case studies. Below are some true color images of some samples where all models failed to predict well. The red circle at the center of each panel indicates the Ayres footprint. And here shows the cases when all models succeed. So you can see that they are undoubtedly easy to distinguish. After looking at multiple examples and performing some aggregations, we can find some common features. First, broken clouds are one of the error sources. This figure shows the percentage of samples correctly predicted by a different number of models within a certain cloud fraction range. So for example, here is the column of clear sky samples. The brown bar shows that about 80% of samples are correctly predicted by all models well, and about 5% where no models predicted well. Except at the boundaries, when the cloud fraction decreases, the error rate will increase. As we can see, blue bars gradually make up most of the column. So one reason is the strict threshold of series models product. Series models product determines a scene to be cloudy if the mean models cloud fraction within the series footprint is larger than 0.1%. So this tiny cloud can make small difference on the spectral radiance over a much larger area. Plus, the collocation of series models clouds is far from perfect as seen in my previous slides. So here we present an example of broken cloud scene. We included the basic information in the title, the true color image, the models cloud fraction color mesh, and the spectrum so that it will be convenient for the interpretation. The black spectrum is the actual spectrum. The red one is the deviation from the mean clear sky spectrum, and the blue spectrum is the deviation from the mean cloudy sky spectrum. It is apparent that the cloud fraction within the circle is small and the spectrum is close to the mean clear sky spectrum, but the true label is cloudy given the threshold of 0.1%. Besides, we also found that low clouds featured by high cloud top temperature and the liquid phase are responsible for many errors, just like the physical algorithms. It is indeed difficult to separate these clouds from clear sky samples due to the overlap in the spectrum space. We also emphasize the data quality issue. For instance, we found that in this case, many samples close to land masses have wrong true labels, like this sample. So from the modest cloud fraction color mesh, it is definitely the clear sky, but the true label is cloudy. The reason why these samples are assigned as cloudy is still unknown and needs further investigation. So in summary, we used machine learning to tackle the clear sky detection problem based on air's thermal infrared spectrum and diagnose these models via feature importance attribution and case studies. We emphasize the value of these powerful tools in physical interpretability. However, as a preliminary research, we might not uncover the full potential of this of the frontier ML techniques. We want to ask, given abundant information in the spectrum, if is it possible for ML models to review more unknown and valuable physical rules to further improve the prediction while avoiding overfitting? And that's all. Thank you for your attention, and I'll take questions.
Thank you so much. Remember to put your questions in Slack channel 3. And while we wait for some questions to appear, let me ask you, Chongxing, have you considered using a two-dimensional CNN? And is that a practical thing to use with a hyperspectral data set where you have so many channels?
Yeah, that's a good question. So we try to limit the information to, we only do the spectral classification. So we do not consider like the spatial pattern or the temporal dependence in the channel. So we pick one sample at a specific pixel, and we only depend on this pixel to determine whether it's a cloudy or clear sky cases. So to improve the performance, indeed, it's beneficial to include the spatial and temporal information. But here we emphasize that we want to dig into the information that could be extracted from the full spectrum, the hyperspectral remote sensing data here.
All right, thank you. Well, I'm afraid we're going to have to move on, but you can put more questions. Just put the speaker's name in your question on Slack, and they can answer it after their session. So now we're going to move on to Daniel Lopez from the University of Illinois, Urbana-Champaign. And Daniel will be talking about generating CloudSat reflectivity using passive microwave brightness temperatures and cGANs.
Here. Okay, right. Hello, everyone. My name is Daniel, and I'm an undergraduate senior at UIUC. And this presentation is a research that I've been working on within the Cloud Systems Research Group here at UIUC, generating CloudSat reflectivity using passive microwave brightness temperatures and conditional generative adversarial networks, or cGANs. So let's start with the motivation for this project. Firstly, passive sensors kind of struggle to observe vertical profiles of hydrometeors, and this includes rain and clouds, where Bayesian retrievals, a standard formulation for rainfall algorithms, have shown to have some model uncertainty and also some associated errors with it. And then secondly, it's known that modern passive sensors can struggle with the retrieval of the cloud profiles. So the big question you wanted to ask here is if deep learning can become a cheaper and alternative approach, which would ultimately allow cheaper and more available passive microwave sensors to determine various cloud properties instead of using expensive radar sensors. And so this figure on the right here gives an estimated mapping of various sensors on their effectiveness on the portion of clouds you can retrieve, with radar giving most information. Then behind it, passive microwave sensors, along with infrared plus visible, and then infrared only and LiDAR only being able to retrieve the very tops of clouds. And so what we're trying to use here is mainly the column in purple, which is the passive microwave. And so as per the title, we are employing the use of cGANs, or conditional generative adversarial networks, to help us with a problem statement. But firstly, I kind of want to go over, if you're not familiar, exactly what is a generative adversarial network, or a GAN. Well, a GAN is a widely used deep learning method for the generation of images and includes two components, the generator and discriminator, both based on convolutional neural networks. And the ultimate goal of a GAN is to synthesize or generate images that cannot be distinguished from real images. And then so generally, GANs have been widely known for the use of lifelike human faces, but we're trying to see here if we're going to apply them to the earth sciences, and specifically meteorology and remote sensing. And so GANs, cGANs, or conditional generative adversarial networks, are different from regular GANs because they can synthesize images based on a specific class. So you can imagine, again, kind of creating images of cars, where a GAN will generate random car images. You can specifically tell a cGAN that you want a specific car class, such as a sedan or an SUV or a pickup truck, which is a pretty interesting thing to think about. And so the image on the right is kind of an explanation about what a GAN does in its architecture, where we start with a random input vector, where the generator starts with the input vector into the generated model. And this generates an output that is compared to a real example of the image in the discriminator. And then into the discriminator model, it compares images and creates a probability of whether the generated image is real or fake. And then based on this probability, we can update both models, applying penalties for misclassified examples and continuing the process for the whole data set. And this kind of goes the same way with a conditional generative adversarial network, or cGAN. The only difference is the conditional vector up on the top right is inserted into the generative model, telling it what class of image to generate. And so we wanted to show some recent success stories of using cGANs and remote sensing for a very similar problem statement. One example was by Luna et al., where they were able to generate CloudSat reflectivity profiles from 4 variables, 4 MODIS parameters: cloud top pressure, cloud optical depth, effective radius, and cloud water path. And the image to the right shows that they were able to successfully create scenes that were able to strongly resemble the real vertical profiles from CloudSat. So the big question you wanted to ask is, instead of using infrared plus visible, what if we use passive microwaves? And this would theoretically give us a larger proportion of retrievable information for the cloud. It might give us a clearer picture and more exact picture of exactly the CloudSat 2D profiles we're trying to emulate. Now we can get to our data sources for this research project. We are using 2 NASA satellites, CloudSat and global precipitation measurement from CloudSat. We are utilizing the 94 gigahertz W-band profiling radar, or CPR. This provides in a long path 2-dimensional vertical reflectivity profile. And then from GPM, we are using the GPM microwave imager, or GMI. This provides a 13-channel from 10 to 183 gigahertz information along a swath path of 885 kilometers wide. Now, kind of an issue within itself is being able to coincide these 2 instruments together for the purpose of creating a deep learning data set. Luckily, this kind of data set exists already in the CloudSat GPM coincidence data set prepared by Joe Turk from JPL in 2016. This data set spans from March 2014 to June 2016 and is matched within 15-minute time intervals. Though one big restriction I wanted to make apparent is that this isn't only a daytime data set, as CloudSat is on an ascending orbit, and this means they can only retrieve data during the day. So ultimately, this model will be limited only to daytime predictions. or accurate daytime predictions. And so this heat map is a distribution of coincident footprints between CloudSat and GMI for our data set. So one of the challenges that we also face here is data variability, where because of the non-synchronous orbit of GPM, we naturally receive more data from higher latitudes far from the equator. And this can create bias issues in the cGAN, but can be rectified through various different methods. One of which I can mention here is like over or undersampling, but those kind of methods also come with associated downsides, unfortunately. And then here is a visual of the coincident path of both CloudSat and GPM for a few frequencies from GMI, noting the differences and ranges for each frequency. The hope is that there's enough information from each frequency to allow us to build a complete picture of the 2D reflectivity profiles from CloudSat. And so this image shows nearly what the actual input data will be when inputting into the cGAN, only instead of feeding it an entire span of each scene, we will be cropping into 64 by 64 pixel chunks. This is where I can also show the use case of a conditional generative adversarial network, where we were able to produce these radar vertical profiles based on a specific GMI scene. So now we can get into specifically more scene results and outputs of our conditional generative adversarial network model. And going from top left column to right and then bottom left column to right, first we see the cGAN not really accurately figuring out the shape of this convective system and overvalues a bit of the actual reflectivity values. Next, to the right of that, also a bit kind of a shape failure by creating some layering of the clouds when it doesn't exist. And also it appeared to have missed the top section portion of the cloud as well. And then the next two models, or the next model after that, the model was actually pretty accurate in determining that there were two cloud layers. Sometimes within the model, there are some cases where the model was actually able to predict these dual layered clouds, but in other cases, unfortunately, the model was also not able to figure out these dual layer clouds. And then, so the next two after that, the model also produced pretty nominal results, getting the overall shape right, but still being a little bit too happy with increasing the reflectivity values within the cloud itself. And so going to the bottom two rows, the cGAN kind of failed to see the upper section of the cloud structure. And the next one, the model got the overall shape right and was accurate in producing the small convective bubbles seen in the bottom right corner and the bottom left corner. And then for the next two, we do see some artifacting, but something interesting in the second from the right was it was really accurate in actually getting the shape right of the overall cloud shape, and also the double cloud layer in the top right of the image as well. And then the last one, this is kind of a little bit of a failure case in determining the vertical location of the cloud. It kind of missed it. And overall, there are scenes where the model is actually pretty great, while in others it has a tendency to be quite inaccurate. The one aspect I found that's kind of hidden, I don't know if you guys noticed, but there's kind of the beginning of a prediction of a bright band shown in the left column, which shows that the model is able to pick up on the characteristics of these highly convective systems, which I think is pretty interesting. Though I should note that these results are quite preliminary and there's still a little bit left we can do to improve the results here, which I can talk about a little bit later. So after going through some specific results, we can go through the entire data set and statistics of the entire data set. So unfortunately, generative models, and especially in our case, GANs, are pretty difficult to evaluate. Nevertheless, we have decided to and found a couple ways to do so. One of which is using contoured frequency by altitude diagrams, or CFADs. These show the frequency of reflectivity values at different heights and then normalized by the total number of samples. And CFADs are helpful because they can show us where the model is biased. In our case, we see the biggest bias at higher reflectivity values, telling us the model is over predicting the occurrence of convective systems at these lower altitudes, which kind of makes sense and fits into the value and fits into the specific scene results that I showed you earlier, where the model was kind of over predicting the reflectivity values within a certain cloud system. And so another metric of accuracy we can use is the evaluation of cloud top heights. From the confusion matrix S graph to the bottom right, we see that the heights are positively linearly correlated, which is the hopeful expected outcome. And overall, we see a mean cloud top bias about negative 105 meters for all scenes. And the cloud top bias was calculated by first determining whether or not a pixel-wide column of the scene contains a cloud, where we know it's an actual cloud prediction instead of an artifact. by checking if two vertical pixels contain non-NaN reflectivity values. And then we average the height of the topmost pixel of all pixel columns and obtain cloud top height for the scene. And one of the benchmarks that we wanted to aim for and beat was the modus retrieval of cloud top heights, which is determined to have an average bias about negative 540 meters. So I believe that the work is on an encouraging path, as we were able to achieve mean bias about negative 105 meters. And so here is a graph going a little more in depth to the relative errors for each cloud top height bin. We see a shift in error from positive to negative as cloud top height increases, where most clouds, this is likely due to biases within the training data set, but most clouds are typically located in the mid to lower troposphere. This makes sense in the air, as we should expect the higher altitude cloud top heights to be underpredicted. But in the future, we will expect to sort out these biases to create a model that is equally capable of producing accurate results for both low clouds as well as high altitude clouds. And then finally, we can go over the main takeaways here. So firstly, our model has capability to produce spatially plausible CloudSat 2D reflectivity profiles based on GMI. And secondly, the model has strong performance when looking at the entire data set holistically, though there are some scenes where the model seems to completely miss the mark, unfortunately. And additionally, there are still improvements to be made in the scope of performing wider parameter sweeps, developing the model trustworthiness, incorporating more values such as modus, and creating more model evaluations and performing more model analysis on why the model is outputting what it is. And so overall and ultimately, given the strength of this project, I believe that the research has potential to showcase the usability performance of deep learning remote sensing, and ultimately the application of conditional generative adversarial networks for the application of computer vision within remote sensing. And so I believe that is it.
All right, thank you so much, Daniel. That was a very fascinating presentation. It's always interesting to see cGAN work in our field. Remember to submit your questions to the Slack channel. While we're waiting for that, let me ask you a question. So did you train over land and ocean? And I'm curious if there was any difference in accuracy as a function of surface type.
So one of the things that we wanted to make sure, or we were limited also by, is that because cGANs are pretty sensitive to noise and there are so many land variations that can be possible, we decided to limit the initial research only to being over ocean. And this would not have to, so we don't have to take care of any basically land noise, and we can just assume that the entire model is only incorporating cloud or reflectivity profiles instead of including land, which would kind of mess up the model because land is variable across the entire world. So it'd make it a lot more difficult, but hopefully that's something that we might include in the future.
All right, great. Thank you so much. We have some questions here. All right, great. Very quickly, how important are the deterministic and stochastic aspects of the predictions? Do you often get very different predictions if you run the cGAN multiple times for the same case?
Yeah, so that's actually something that we wanted to look for in the future. One of the things that we're specifically interested in and making sure we get correctly is determining model trustworthiness. So one of the things that kind of was incorporated into a model, or we hope to incorporate in the future, is basically the variability within the cGAN, because one thing we want to make sure is that this model is actually something we can trust. And so one of the things that might happen within some cases is that the model might just get lucky for a specific case, and it's actually not based on any physical and real parameters. So one thing we want to try to do is basically run the model a bunch of different times, look at the same case, and see how variable it is. And this would help us determine whether or not this is something that's actually based in physical reality or just something that basically we're getting lucky with. So it's something we want to test in the future.
All right, thanks a lot. We need to move on now to Janni Yuval from Massachusetts Institute of Technology. He'll be speaking about neural network parameterization of subgrid momentum transport learned from a high-resolution simulation.
Okay, thank you. And I did work with Paula Gorman, and I want to start by kind of motivating why I think we need machine learning parameterizations. And I'm showing here a caricature of a climate model. And nowadays, we still have a lot of inaccuracies in climate models and a lot of uncertainties in climate projections. And mostly you can track down these uncertainties and inaccuracies to the representation of small grid or subgrid physics or small scale processes. And to be explicit, what I mean by subgrid processes, if we have our caricature for climate model, we typically want to incorporate the laws of physics in the model. But if we think of what the grid, the resolution that we actually are able to resolve, and we zoom in, typically climate models resolve nowadays somewhere between 50 to 100 kilometer grid boxes. So everything with a smaller scale, we just don't represent explicitly. So you can think, what do you have in 100 by 100 box in the atmosphere? You have clouds, you have radiation, turbulence, convection, many processes, and we cannot just ignore them and say, okay, we cannot represent them. What we do, we try to represent them by using kind of simplified models we call parameterizations. So we have typically how it is done, we have experts coming and having some conceptual model of each process, having some kind of simplified mathematical representation for this process, and use this kind of parameterization in climate models. So we've gone quite a lot of since, let's say, the 70s, and we improved these parameterizations, but still we're in this unsatisfying situation that we have a lot of inaccuracies in climate models, a lot of uncertainties in climate projections. And in recent years came this idea to use a different approach to parameterization. And this approach is relying on the fact that nowadays we can run high resolution models that can resolve some kind of small scale processes like convection, to some extent turbulence and so on, use these high resolution models to somehow learn a new representation, which is a data-driven representation, what I'm calling here a machine learning parameterization, eventually implement in a climate model, and of course still use the laws of physics where we can. And our hope is this kind of machine learning parameterization will be much better than our current parameterizations. So in recent years, there have been several attempts to build this kind of a hybrid system that kind of combines a climate model or atmospheric model with a machine learning parameterization. And this kind of tries had a lot of interesting outcomes, some successes, but some also reoccurring features like unstable simulations, so literally numerical instabilities, so the model failures and so on, some kind of a climate drift. You start with one climate, the climate just drifts, and sometimes you need to remember maybe that this machine learning parameterization do not obey physical constraints, at least not automatically. And you can already imagine if they don't obey physical constraints, how can, let's say, you can get to a climate drift, you inject, let's say, too much energy at every time step, for example. And in a recent, in our two previous work, what we have achieved is kind of, we achieved that physically consistent parameterizations that learn from a high resolution model. Here I'm showing a snapshot of a high resolution model on the left, the color indicating precipitable water. So it's kind of latitude versus longitude snapshot of a high resolution model. And what we showed that we take this kind of a high resolution model and we can learn a new representation, a machine learning representation that leads to stable and accurate simulations. And let's see how it works. Just as an example, so this is a snapshot from a high resolution model. We run the exact same model at a coarse resolution. This is what we get. This is pretty different. So what's the difference? The main difference that you can see here, the structure in the tropics is completely different. In the coarse resolution, we have a single ITCZ. High resolution has double ITCZ, or this kind of rain bands where we have a lot of moisture. And when we run a coarse resolution simulation with a machine learning parameterization, we get statistics which is very, very similar to the high resolution case. So this is kind of the dream of parameterization, that we would be able to run a low resolution model but get the same statistics as a high resolution model. So all these parameterizations that I've talked to you about, also what we have done so far, have kind of used this kind of idea, take a high resolution model, but what they have learned so far is just the effect of subgrid processes, these small scale processes, on the moisture and thermodynamic variables. But something is still missing, because we know that momentum is also affected by subgrid processes that we don't resolve. So let's, as an example, let's look at two such processes. One is convection. So convective momentum parameterization, this is kind of a caricature of convective momentum parameterization. So we have convection occurring, takes the horizontal momentum upwards. And we know that convective momentum parameterization affects the Hadley cell, precipitation distribution, sea surface temperature, a lot of important quantities that we want to get correctly in simulations of climate. And not only convective momentum transport we have occurring in, which is subgrid in current climate models, we have also gravity waves. Here you can see these kind of nice stripes in the clouds. These are gravity waves, and they have gravity waves affect a lot of the circulation in the stratosphere, QBO and other processes that are occurring in the stratosphere. So basically, if we want to have a complete climate model, we really need to get also momentum parameterization correctly. So first, I'm going to present is our parameterization and how we learn from a high resolution model this kind of momentum parameterization. But first, I just want to focus on how we take this high resolution model and what do we learn from it, what do we try to predict. So just to give an example, here I'm plotting a surface zonal wind for this high resolution model. So it's latitude versus longitude. And I'm zooming into a small section, which is a roughly 100 by 100 kilometers. So this is typically the grid size in a climate model, and you can see that you have like some positive wind, some negative wind. If you ask yourself, how would a climate model look like for this region? It would look like that, maybe slightly negative, maybe zero wind, because you can think it would just average this region roughly to represent what's happening here. So how we define the subgrid processes that we are learning, I'll give you an example for a single process that we are learning at first, which is subgrid vertical advection. So to calculate the subgrid flux due to this process, we basically take the high resolution vertical wind W, multiply it by the high resolution zonal wind U, and coarse grain it, or horizontal average. This, in theory, this is how we would like to run our climate model with, but we are not exposed to these high resolution quantities. What we are exposed when running a climate model, we are exposed to the coarse grained vertical wind and the coarse grained zonal wind. And the difference between these two quantities is what we define as subgrid flux. And I'm insisting on calling it a subgrid flux because when we are predicting fluxes, we are guaranteeing that we are conserving momentum because we don't introduce sources or sinks of momentum. And you can read more in this preprint that I'll show in the next slide how we do it. But this is basically what we're trying to predict using a neural network. And let's see how it works in practice. So we are training this kind of a neural network to predict momentum fluxes. And on the left here, I'm showing a pressure versus latitude plot of the subgrid momentum fluxes, what our climate model does not resolve. So this is the mean. And in the right, I'm plotting the mean taken from a neural network. So you can see they're pretty similar. In the tropics, we have upward transport. In the exotropics, downward transport. You want to get a hunch, why is it different in the tropics and subtropics? I'm plotting here on contours how look the wind shear. So basically, we have a downward transport. The shear is negative in the tropics, so we have upward transport, at least on the mean, and the vice versa in the exotropics. So this is great. In the mean, the neural network is doing what we expect it to do, but let's look at really the skill of the neural network. Let's look on how well it can predict zonal momentum fluxes. So here I'm plotting the coefficient of determination, or R squared, for pressure versus latitude. 1 means perfect prediction, 0 mean we are as skilled as just guessing the mean. And you can see that we are not very skilled actually, especially if we compare to how well we are able to predict moisture transport. So this is an interesting from a physical perspective. Why is it difficult to predict zonal momentum fluxes, even when we use a data-driven approach? And this is my next slide, try to explain why it is difficult to predict this kind of fluxes. To do that, I'm showing here a plot of precipitation amplitude versus time for a single grid point in our high resolution simulation. Below, I'm plotting here the subgrid moisture fluxes. And in the bottom panel, I'm plotting the subgrid momentum fluxes. And I just want to concentrate in this box. So what we have here, we have two precipitating events. Those are convecting events. You see that during these events, we have basically moisture is transported upwards. But momentum is transported both upwards and both downwards. So it is well known that convective momentum transport can be both positive and negative. The blue line shows the average convective momentum transport can be all positive or negative during convection events. This is due to the shape of clouds. So basically what we think, it's very difficult for a neural network to get correctly the shape of clouds. So it doesn't know even if the transport should be negative or positive. And in the second point, we show that it's pretty difficult to get correctly how gravity waves affecting the circulation. And we know, at least from theories, that linear gravity waves can transport momentum, but they do not transport conserved thermodynamic variables like, let's say, a conserved energy variable. So, okay, this is kind of disappointing, but still we have some skill, so we can try to implement it in our model. This is the true test of our parameterization, making this hybrid system, and let's see how it looks like. And I'm concentrating on a single variable to show the result, the surface meridional wind. And the reason that we focus on the surface meridional wind is that we know convective momentum transfers affect surface wind, and it's really important for the simulations of climate to get the surface wind correctly. It affects the exchange between ocean and atmosphere and so on. So first plot, I'm showing latitude versus amplitude for the high resolution. This is the best we can get. This is what we want to emulate. The second plot, I'm showing just a low resolution model, the exact same model. How would the surface wind look like? And you see it's pretty different, especially in the tropics, also in the extratropics. The third plot, I'm showing a simulation that it has a low resolution, but has a neural network parameterization, but only for moisture and thermodynamic variables. So it leads to a stable simulation. This is important. We can talk about statistics. We don't have blowups. And you can see that it already improves the representation of surface wind in the tropics, still not very well in the extratropics. But next, we're going to look what happens when we take a low resolution model, but try to use a neural network for all variables, learning the effect of these subgrid processes on all the variables, including momentum, moisture, thermodynamic, and we see how it corrects the biases. So the red line is basically closer to the black line. The black line is our target, is our high resolution simulation, which we want basically to be able to emulate, to run a low resolution and get the statistics as a high resolution. You can see the red line is very similar already to the black line, especially in comparison to the other two simulations we ran. So just to give a summary, we use a high resolution model to learn a physically consistent momentum conserving neural network parameterization. We discover it's pretty challenging to predict correctly subgrid momentum fluxes, but eventually we see that we can improve the simulations even when we build this hybrid system of atmospheric model and machine learning parameterization. It still improves the simulation of surface wind and other variables which I didn't have time to talk about.
All right, thank you very much. Very interesting talk. Remember to submit your questions via the Slack channel. I wanted to ask you, so you mentioned that machine learning doesn't obey conservation laws and how you handled that, but did you find any difficulty learning the correct direction of causality? Did your network at all get confused by that?
So how we design it, we don't like how we verify that we conserve quantities like energy, moisture, momentum, and so on. We basically somehow design the outputs that they predict something that basically have to obey. Flux was just a single example. I mean, most people have so far predicted tendencies. If you integrate tendencies vertically, you can get a non-zero results. When you do it for the fluxes, you will get a zero result because you won't have fluxes in your boundaries. But other processes, we have a manuscript in GRL that we describe basically process by process how we do it. It's kind of designed per process, how to kind of inject our physical priors into the parameterization, rather really changing the structure of the neural network, which some people did so far. And we find it pretty, we find it that it's pretty useful to kind of design what you want to predict rather than changing the architecture, but maybe changing the architecture to somehow making it much more fancy, and kind of Bayes rules would be as good. I don't have a baseline to compare yet.
Okay, thanks a lot. You can keep submitting questions on the Slack channel, but we have to move on now. Our next speaker is Linsey Passarella from the University of Tennessee, Knoxville. And she will be speaking about super resolution reconstruction of E3SM data using FSRCNN.
Okay, so yeah, my name is Linsey, and I'm going to talk a little bit about this super resolution project I was working on. So why is this important? I think a huge challenge we face with climate data is a lack of high resolution data. And that is really important for assessing the risk of climate change in local and regional scales. And recent advances in computing resources have allowed for these ESMs to be run at high resolutions. However, a lot of them are prohibitively expensive. You need a supercomputer to even run them, and they produce terabytes and terabytes of data. One approach to getting this high resolution data is to use statistical or dynamical downscaling. So for example, bicubic interpolation. And so we we are kind of focusing here on the statistical downscaling aspects. So mapping coarse resolution data to a higher resolution map. And then there have been recent studies that have used machine learning techniques for statistical downscaling, such as neural networks, support vector machines, GANs. And so we're focusing on, a deep learning technique called super resolution convolutional neural networks. And so this was developed, I think, in 2016. However, one issue with this approach is that it requires a bicubic interpolation step before you run it through the convolutional neural network. And so that creates a lot of weights to train. And so it can be, again, computationally prohibited if you don't have the correct GPUs, CPUs to run it. But another researcher developed a method that he termed a fast super resolution convolutional neural network, an FSRCNN, that alleviates this pre-processing step and replaces it with a deconvolutional layer at the end. And this lowers the cost of the networks significantly, almost by a factor of n to the power 2. So we're going to use this FSRCNN approach to downscale some E3SM data that we have. I don't know why my computer, okay. So for this study, we're looking at a monthly output of 30-year data from a 1950 control simulation with a global high resolution E3SM data. And one of the things we can think of when we're using gridded climate data for downscaling is we can think of the grids as pixels. And specifically, we can think of them as grayscale pixels, which makes training a lot easier because we're not focused on a 3D convolutional neural network where you're looking at the 3 different color channels. So that can kind of simplify things as well. And so we choose our 5 variables to test our FSRCNN approach. We want to look at surface temperature, shortwave heat flux, longwave heat flux, and then 2 types of precipitation. So convective rate and large scale rate. So this in total is 1,800 images and 360 images for 1 variable. It's important to train these models on multiple different types of data. You get a more robust model that way. And we want to look at also, so we have surface temperature, which is a very spatially uniform variable. And then we also have our precipitation variables, which are less homogeneous. And so we want to see how well our model does on both of those types and how well it can reconstruct those finer high resolution details. So for our 1,800 images, we split it into 90% training and 10% testing. And we make sure to keep that ratio for each of the variables as well. So we have the same number of variables for each of our like temperature, heat flux in our training and our testing data sets. So this is a look at our architectures, and it's a little bit confusing, but here we see the SRCNN. So this is the basic architecture that we're looking at. So it takes this low resolution image, so 60 by 60. You have to do this pre-interpolation step to get it to be 240 by 240. Then we run it through a patch extraction, nonlinear mapping, and then we get to our final high resolution reconstruction. And now this is the FSRCNN proposed by Dong et al. In 2016. And so you can see that it takes this low resolution image and passes it through convolutional layers as is until you get to this deconvolution step where it then reconstructs the high resolution image. However, what we found is when you go from this 60 by 60 feature map and try to get straight to the high resolution image, you get this checkerboard pattern because there isn't enough data to reconstruct, there isn't enough information to reconstruct this high resolution image. That could be because we're interpolating it to a higher degree than Dong et al. Initially proposed. So what we did, and what we're calling our FSRCNN ESM, is that we added a patch extraction and nonlinear mapping step before going to our high resolution, our final high resolution image. And this is after the deconvolutional layer. And that just gives it a bit more information to reconstruct our high resolution data from. So when we look at our reconstruction evaluation, we can look first at our cumulative CPU training time. And so we see that our FSRCNN, despite the fact that we added those 2 layers at the end, is still taking a smaller amount of time to train than our regular SRCNN, excuse me, while achieving the same amount of loss in our training data set. We can also look at our L1 and L2 errors. So this is the L1 error for our FSRCNN ESM as compared to SRCNN and also bicubic interpolation. And so we can see that it's performing better there, also within our L2 error. And then over here, we're looking at our peak signal to noise ratio, which is a typical metric used when looking at image reconstruction. And so we can see that for most variables across the board, our FSRCNN ESM is performing better than those other two reconstruction methods. However, for surface temperature, we get that our bicubic is working better than both of our machine learning methods. And one reason that could be happening is because surface temperature is very spatially uniform. And so there's a chance that our SRCNN and FSRCNN is overfitting those weights and kind of overthinking the reconstruction, I guess. So this simple bicubic interpolation method worked better there. We also want to note that for our precipitation variables, they all generally showed lower reconstruction value, but that is kind of expected given that precipitation is a nonlinear process. It's multi-scale, multi-phase, and so that's generally going to be harder to reconstruct overall. And then we can look at our visual reconstruction. So this is from a sample in January and a sample in June. So this first line is our first variable for surface temperature. So this is our low resolution image. This is what it looks like when you do bicubic interpolation. This is the outcome of our SRCNN. And then this is our FSRCNN ESM. And then our ground truth high resolution image. So we can see that across months and across variables, if we go down here to our fluxes and then our precipitation data, that our FSRCNN visually reconstructs the data better than the bicubic interpolation and SRCNN. And that's the same for June. So generally across time periods and across variables, this is reconstructing the data better visually as well. So just 3 key points to take away from this this work. So we present a novel approach for downscaling gridded climate data. And this is, again, based on the FSRCNN, but we kind of tweak it to fit our data. It was able to reconstruct high spatial resolution patterns, again, except in that temperature variable, but we think it's due to overfitting when we have such a complicated neural network that's trying to learn a very spatially uniform variable. And it is less expensive to train over those other machine learning methods as well. So that's all from me, if anyone has any questions.
Yeah, thank you, Linsey. We already have a couple questions. First of all, are you using PyTorch or TensorFlow?
I'm using TensorFlow.
Okay. And another kind of related question, I suppose, is can you tell us more about the computing hardware cluster that you used for training these models?
Yeah, so I have access to Cori supercomputer out at NERSC. So I use one of their CPU. They have Jupyter login nodes that you can use on Python. So I use one of their login nodes through Jupyter.
All right, great. Another question, did you standardize your data sets before training?
Yeah, we standardized to a min-max scaler, so between 0 to 1. And that, again, makes it kind of similar to if you were training grayscale images, and it makes it really easy to train.
Okay. And another question about whether you use single variable images. Did it work? Sorry.
For the first question, the single variable images, they are, except we train it with 5. We randomize those 5 different variables within it. But when it's looking at a single image, it's a single variable.
Great. Let's see, you can submit your questions to Slack channel 3. I did want to ask you, with getting sharp results out of CNNs, an important thing is the loss function. Did you find that you had to do any special work on the loss function?
No, we did most of our work on just tweaking the architecture to get what we wanted. But mainly, I believe we used a mean squared error loss function, and that worked for our data.
All right, a follow-up question about the standardizing. Was it monthly or seasonal or annual standardizing?
We used monthly standardizing.
And another question, what was the accuracy of your model?
Yeah, so we can see it. For this one, we're looking at mean squared error. So we're not looking at accuracy values as much, but we get a very low mean squared error loss, which we can also look at for our L1 error. So a majority of it is less than 0.1. So we can say that about 90% performance there.
All right, great. If you have additional questions, please send them to her in the Slack. Up next, our last speaker of the day, of this session, I should say, is Spencer Clark from NOAA GFDL. And he'll be talking about applying machine learning parameterizations to coarse graining to improve the skill in simulating multiple climates in a full complexity GCM.
Thank you. Let me share my screen. Okay. Yeah, so today I'm going to be talking about work that I've done in collaboration with my team at the Allen Institute for Artificial Intelligence. And I'm also affiliated with the NOAA Geophysical Fluid Dynamics Laboratory. So I'd like to acknowledge them for some of the computational resources that they provided for this work. And yeah, so motivation for this project stems from recent advances in machine learning methods for improving the simulation of climate of coarse resolution models. So this first started with work in an aquaplanet model by Noah Brenowitz while he was a postdoc at the University of Washington, and it's also been pushed ahead by Janni Yuval at MIT. And the basic premise is that while fine resolution models require fewer parameterizations and therefore might have less structural uncertainty than coarse resolution models, they're quite expensive to run. And ultimately, it would be great if we could run models at coarse resolution, but simulate climate changes like fine resolution models. And so recently, our group at AI2 presented an approach that for the first time achieved improvements in the simulation of the spatial pattern of precipitation in a coarse resolution model by learning from a 40-day full complexity global 3-kilometer resolution simulation. And the objective of this work is to kind of take things one step further. So here, we'd like to use training data from multiple fine resolution simulations instead of just one to build a set of machine learning models that improves coarser resolution simulations in multiple climates. So I'll briefly describe our approach now, which is largely an extension of our work in with the 3-kilometer reference simulation. So we start by running reference fine resolution simulations in multiple climates using NOAA's FV3GFS model. And we modify the climate by perturbing the sea surface temperatures that are prescribed by a constant value. So for the work that I'm presenting here, this is either -4 Kelvin, no perturbation, +4 Kelvin, or +8 Kelvin. And in contrast to our previous work, we run these simulations for 2 years, each to generate training data around the annual cycle, and also give us one independent year to test our approach against. And in addition, we elect to run these simulations at 25-kilometer resolution, and this allows us some more freedom to prototype before committing to running multiple multi-year global 3-kilometer resolution simulations, which would be quite expensive. So in each of these runs, we store outputs of the model state coarsened by a factor of 8 to 200-kilometer resolution every 15 minutes. And so 200-kilometer resolution is our target coarse resolution for this particular study. So next, what we do is we run simulations at this target resolution that are nudged to the coarse and fine resolution models, temperature, specific humidity, horizontal winds, and pressure. And then by saving snapshots of the nudging tendencies in the accompanying coarse model state, we build a data set of state-dependent bias corrections that we can then machine learn. And in addition, since the coarse surface radiative fluxes predicted by the model physics are biased, we prescribe those from the coarse and state of the fine resolution model, with the eventual goal of learning those as a function of the coarse model state as well. So once we generate that data, we can then train machine learning models to predict the nudging tendencies and surface radiative fluxes. And so while we've experimented with predicting the nudging tendencies for the horizontal winds, for this work, we'll focus on learning only the temperature and moisture nudging tendencies, and then also the surface radiative fluxes. And so the last step in this process is then testing our machine learning models by running them online and free running simulations and seeing if they improve the simulation of climate over coarse resolution simulations without any machine learning corrections. So I'll present some results of that at the end of this talk, but for now I'll go into a little more detail about our machine learning. So to predict the temperature and moisture nudging tendencies at each vertical level in the column, we use a neural network. So our training data set consists of about 2.2 million columns that are selected randomly from the first year of each of the 4 nudged simulations. So basically we're combining all the data from all the climates together in our training. And because of this, our hope is that our resultant model should be applicable in all climates. And so we use the column temperature profile, column specific humidity profile, cosine zenith angle, and surface geopotential as inputs. And then we output the column profiles of the nudging tendencies. And then also to estimate the sensitivity to the initial weights of the network that are randomly chosen at the start of the training process, we generate and then later run with neural networks that are initialized with 4 different random seeds. So take a look now at how these networks perform offline. So one thing that stands out if we plot some vertical transects of example nudging tendencies is that they're noisy and therefore they can be challenging to predict precisely. So here the left column represents the instantaneous nudging tendency along the prime meridian for a random time in the second year of the nudge run in the unperturbed climate. And the top row is the temperature tendency, and the bottom row is the moisture tendency. And the right column represents the prediction by one of our neural networks. And so we can see that while the small scale features are generally not captured, the broad picture is somewhat consistent. And so this is reflected a little bit more clearly if we take a mean over all the columns in our test data set and a mean over all the predictions. So just to show that we capture the range of nudging tendencies across the different climates, I've separated out the minus 4K and plus 8K components of the targets and predictions. So these are the blue and the red curves respectively. The left panel is the temperature tendency and the right panel is the moisture tendency. And the solid line is the target and the dashed line is the prediction. And particularly in the case of the temperature tendency, the same network's able to predict things in the minus 4K and plus 8K climates pretty well. But if we look at the moisture nudging tendency, we see that the network does slightly better for the cold end of the training range than the warm, where it largely underpredicts this sort of large drying tendency in the boundary layer. But moving on, to predict the surface radiative fluxes, we use a random forest. And so while we've experimented with using a neural network, we found empirically that a random forest works best when we apply it online. So the training data set's the same, but in this case, we're predicting the downward shortwave, downward long wave, and net shortwave radiative fluxes at the surface. And so as inputs to this model, we use the same inputs that we used for predicting the nudging tendencies, but then we also add in the surface albedo and the land sea mass. And with this model, we're able to predict these surface radiative fluxes pretty well. So here I've plotted some instantaneous targets and predictions from the testing data set. So the top row is the target and the bottom row is the prediction. The left column is the downward long wave radiation at the surface, middle columns downward shortwave radiation at the surface, and the right column is the net shortwave radiation at the surface. And we can see that we can capture even some of the fine scale spatial structure of these fields in instantaneous snapshots. We've shown that our models work reasonably well offline. How do they perform when we plug them into the 200-kilometer model? So to test whether our machine learning models improve coarse resolution simulations, we start by running 200-kilometer resolution simulations without any machine learning in each of the climates. And we run these for 5 years each, and this allows us to get some sense for the spread of errors relative to the 25-kilometer resolution reference runs. And then we run machine learning corrected simulations in each climate for 1 year with the neural networks trained with the 4 random seeds. And so this gives us some sense for the spread and error metrics when we're using networks trained with different random seeds. And then finally, we compare the error metrics relative to the fine resolution runs between the baseline and machine learning corrected cases, and we see what impact the machine learning has. So the first metric that we'll look at is the root mean square error of the annual mean surface temperature relative to the fine resolution reference. So on the left, I'm plotting the spatial pattern difference in the time mean surface temperature and the unperturbed climate between the coarse and fine resolution runs. The top panel is for the baseline configuration, and the bottom panel is for the machine learning corrected configuration. And so here we can see that the baseline model is generally too warm in the tropics and mid-latitudes and too cold in the polar regions. And the machine learning acts to correct both of these biases, and in turn reduces the root mean square error over land by about 35%. And the spatial patterns of the bias look similar in other climates, so that's why I'm only showing the maps for one climate here. And on the right, I'm plotting this root mean square error metric for each year of each baseline run in each climate. So these are the blue dots. And then also plotting this metric for each random seed configuration for each machine learning corrected run in each climate. So these are the orange dots. And so here we can see that while one of the random seeds tends to be at the bottom edge of the range of the baseline runs, machine learning seems to fairly robustly improve the surface temperature bias of the coarse model in all of the climates. But one caveat here, which is going to apply in future slides too, is that you might notice that there's only 3 dots that are machine learning corrected in the -4K climate, and this is because one of those simulations crashed due to numerical instability. But if we move on to precipitation, we find that machine learning has less of an impact, particularly at the warmer edge of our training range. So again, the left column is showing the bias relative to the fine resolution run in an unperturbed climate. And so here we see that the ML does a good job of correcting the negative precipitation bias over tropical South America and Africa, but it overcorrects a warm bias or a positive bias in the Western Pacific warm pool region. And in the net, this leads to a modest improvement in global precipitation root mean square error in the -4K unperturbed and +4K climates, but precipitation RMSE is not improved in the warmest climate. But another attribute that we seek to improve via machine learning regarding the precipitation rate is the land mean precipitation bias. And we can see in the upper panel on the left that in the unperturbed climate, there's a substantial bias in the baseline model, about -0.8 millimeters per day. And this is particularly due to the negative biases in the tropical land regions that I mentioned earlier. And in all climates, our machine learning helps to improve this. So our machine learning corrected runs generally have much smaller magnitude positive bias of around 0.1 to 0.2 millimeters per day. And so this improvement in the precipitation bias over land can in part be attributed to improving the surface energy budget through predicting an unbiased net radiative flux into the surface. So this feeds back with the evaporation rate and ultimately the hydrological cycle. So this plot on the right here shows that our machine learning corrected runs are significantly less biased in this regard than the baseline runs. So in conclusion, we've shown that it's possible to train machine learning models that can be applied in multiple climates that improve the simulation of surface temperature and precipitation rate in a coarse resolution model. And we found that our skill in improving the precipitation decreases towards the warm end of our training range. And so this was one reason why we included the plus 8K climate in our training, but this did also have this negative side effect of introducing an unstable seed in the minus 4K climate. And then finally, while I didn't show it specifically, we found that predicting the surface radiative fluxes was needed to obtain unbiased land precipitation rates and improvements to the surface temperature. So with that, I'll take any questions if we have time.
All right, thank you, Spencer. Yeah, we do have a question here. In the 2021 GRL paper, the ML parameterization used led to large deviations in stratospheric temperatures and some other fields as well. Do you have similar biases here? If not, what did you do to remove those large biases?
Okay, so here we don't have quite as large biases in the stratosphere. One of the reasons for that is actually that we're no longer predicting the momentum nudging tendency. So we found that that was something that was contributing to the large biases in the stratosphere. So yeah, that would be my answer to that question. Okay, great, thank you. If you missed a talk that you would like to see, all the recordings will be made available in about 2 to 3 week time period. This session will be continuing at 2:15 this afternoon. Right now, we have a virtual coffee break, and Yoonjin Lee has posted the link in the Zoom chat. And so thank you, everyone. I'd like to thank all of our speakers for some very interesting talks. Thanks also for staying on time. You're a really great group. And have a good meeting, everyone. Bye-bye.